All right, so did you have any specific questions that you wanted to go over before I just to start to go through some of the questions in chapter 2? Was there anything specific that you wanted to ask or go over?
Not at the moment. I just want to see for the lecture, and then if I have any questions, I will.
Okay, no problem. And Kim's just joining, so let's just give her a second.
Hello.
Hi, Kim. How are you?
Good.
Good. So I was just asking Geraldine, is there anything specific questions that you want to go over before I start going through some of the questions in chapter 2?
I don't think so.
Okay. All right. So then we could just start to go through some of the stuff in chapter 2. So the first thing I thought I wanted to touch upon a little bit was determining significant figures in a measured number. So essentially, your measured numbers are determined whenever you use some sort of measuring device, like a ruler, like a thermometer, a balance, graduated cylinder, basically anything of that nature to figure out a measurement. The digits that are there essentially are classified as significant figures. What it really comes down to, for the most part, is that it's about the zeros. Because really the first rule of significant figures is that all digits other than 0 are always significant. So basically 1 through 9, no matter where they are in the number, before the decimal point, after the decimal point, they are always going to be significant. So what it comes really down to is the zeros. So essentially, zeros in between two non-zero digits and zeros after the last non-zero digit that fall to the right of the decimal point are significant. So anytime you have zeros in between two non-zero digits, again, whether the non-zero digits are before the decimal point, after the decimal point, or you could have one non-zero digit before the decimal point and another one after the decimal point, and the zeros in between them would actually be significant. And then the other place, in a sense, where zeros are significant is that if you have zeros after the last non-zero digit, and those zeros also fall to the right of the decimal point, then those zeros are significant as well. Then essentially, zeros before the first non-zero digit are not significant. And essentially what those zeros are sort of determined to be is that those zeros are sort of determined to be placeholders. They're just basically sort of used in order to make the number go out to the number of decimal places that it needs to be. So in the world of significant figures, all zeros before the first non-zero digit are not significant. And again, the reason why is they're considered to sort of be quote unquote placeholders to get you out to whether it's the hundredths place, the thousands place, the 10,000s place, however far out you have to get in order for the number to sort of be written down. The final point has to do with whole numbers. Okay. If the zeros in a whole number, and again, these would be after the last non-zero digit, are followed by a decimal point, they are significant. If they're not followed by a decimal point, then those zeros are not significant. And the example that I commonly give to sort of illustrate the difference is the example of 15,000 grams versus 15,000 decimal point grams. Because honestly, you know, when I sort of look at these two numbers, I don't really see much of a difference between them. But in the world of significant figures, there is really a big difference that exists. And one of the ways to think about significant figures is that essentially they include all of the certain digits and the first estimated or uncertain digit. In the first example, 15,000 grams without the decimal point, you only have two significant figures. Because in this case, only the 1 and the 5 are significant. So what does that tell me? It tells me that the first estimated or uncertain digit, the last significant figure, is the 5. So in other words, is it really 15,000 grams? Or is it 14,000 grams? Or is it 16,000 grams? That's essentially where the estimation is made. However, when the decimal point is there, well, that tells me that the 0 at the end is the first estimated or uncertain digit. So in other words, is it 15,000? Or is it actually 14,999? Or is it 15,001? So in the first example, I made my estimate essentially in the thousands place. In the second example, where you would have 5 significant figures, the estimation is made in the ones place. So that's a big difference between them. And that in reality is the difference between having a whole number, the zeros in a whole number being significant or not. The other thing just to mention is that if we actually had 15,000 decimal point 0 grams, then this number here would have 6 significant figures. And the reason why would be is that essentially this 0 on the end is after the last non-zero digit and is to the right of the decimal point. So that 0 would be significant as well. So the decimal point there would make all the zeros to the left of the decimal point after the 5 significant, sort of like the whole number idea. But then the 0 after the decimal point would be significant because it's after the last non-zero digit and to the right of the decimal point. All right. Any questions about that? All right, so let's just do a couple of examples. So what we want to do here is just give the number of significant figures in the following measurements. And let's see, indicate at the zeros. So this essentially would be, I'm going to take a look at problem 210, chapter 2, problem 10. So the first one we have is 20.60 milliliters. So how many significant figures would we have in this number? Well, first off, the 2 and the 6, they would definitely be significant because essentially all numbers other than 0 are always significant. The 0 in between the 2 and the 6 would be significant because all zeros between two non-zero digits are significant. And then the 0 after the 6 would be significant as well because it's after the last non-zero digit and it's to the right of the decimal point. So in this example here, you would have 4 significant figures. Let's take a look at letter C, which is 4.00 meters. So essentially, how many significant figures would you have in this number? Well, the 4 would definitely be significant because it's not a 0. So the question becomes, what about the 2 zeros? And in this case, for the 2 zeros, the answer is absolutely yes. Those zeros are significant. Again, what sort of rule leads us to that conclusion? That they are after the last non-zero digit and they fall to the right of the decimal point. And therefore, this number here would have 3 significant figures.
Okay.
Okay. Do letter E, which is 60 eats, then 2 zeros, and then 3 more zeros, and grams. So it looks like we have 608 million grams. All right. How many significant figures would be in this number? Well, first off, the 6 and the 8, they would definitely be significant. The 0 in between the 0 in between the 6 and the 8, that would be significant as well. But the rest of the zeros, 5 zeros after the 8 here, would not be significant. Because here you have a whole number and there's no decimal point given. The fact that in the world of significant figures, when you have a whole number, when there's no decimal point given, that's important. So in fact, the 5 zeros after the 8 here would not be significant. So how many significant figures do you have here? You only have 3 significant figures.
I know it's not really important, but your comma's in the wrong spot.
Oh
By
yeah,
the 8.
actually 60,800,000. No, that's important. Thank you. Tells you I haven't put in too many commas.
Yeah.
Years, but you're right. Yeah, 60,800,000. That's better. Thank you. So definitely 3 significant figures, though. Doesn't change it. That's
Okay.
Thank you. All right. Take a look at one more. So this one here, want to just point it out. So 5.0 times 10 to the minus third liters. Because on occasion, you're asked to give the number of significant figures in a number written in scientific notation. So this is a little bit different. All you really have to remember is that when you have a number in scientific notation, the number of significant figures is equal to the number of digits in the coefficient. Now remember, when you have a number in scientific notation, there's always 2 parts. There's the coefficient, and then there's essentially the power of 10. To figure out the number of significant figures in a number in scientific notation, all we have to do is look at the coefficient. How many digits are there? In this case, there are 2 digits. there's a 5 and a 0. And therefore, what that tells us is this number is going to have 2 significant figures. That's it. All right, so just keep that in mind when you're looking at a number in scientific notation. All right. So that was the first thing I wanted to spend a little time talking about this evening. All right. So the second thing I wanted to spend some time talking a little bit about were adding, subtracting, multiplying, and dividing, and coming up with an answer with the correct number of significant figures. Basically, we can break this down into 2 sort of categories. The first one would be addition and subtraction. So for addition and subtraction, if you're looking to give the answer with the correct number of significant figures, your answer should go to essentially the highest decimal place of the numbers that are given. And in a moment, I'll show you what I mean. When I think about decimal places, on the left side, you have thousands, hundreds, tens, ones. And on the right side, you have the 10th place, the 100th place, the 1000th place, the 10,000th place. Basically, from my perspective, as you go from left to right, in other words, thousands, hundreds, tens, ones, and then tenths, hundreds, thousands, you're going lower and lower. The number is becoming lower and lower. As you go the other way, in my mind, you're going to a higher decimal place because you're going to a higher value. So basically, your answer should go to the highest decimal place of the numbers given. So for example, if let's say you have 28 centimeters plus 4.056 centimeters plus 1.23 centimeters. When I look at these 3 numbers and I say to myself, okay, what is the highest sort of decimal place of the numbers that are given? So when I look at this, I say, okay, for 28 centimeters, the last decimal, and maybe you'll want to add the caveat, the last decimal place of each number. So your answer should go to the highest decimal place. And let me tweak the definition a little bit. Just to make sure we're totally clear. Okay. So the answer should go to the highest decimal place of the last decimal place of each number. So let's really clarify that. So if I look at 28 centimeters, the last number, the 8, essentially is in the ones place. If I look at 4.056 centimeters, the last decimal place, tenths, hundreds, would be the thousandths place. And when I look at 1.23 centimeters, I look at the last decimal place. The last decimal place would be the hundredths place. So when I give my final answer here, my answer should go to the highest decimal place of the last decimal place of each number, which means out of these three, the last decimal place, which one has the last decimal place at the highest value? In the ones place. So when I give my answer should be to the ones place. Now, what the textbook talks about is that if you're rounding and you go and you're going to round using 4 or lower, you stay at that number. And if it's 5 or up, you go to the next number. That's what they talk about in terms of rounding. So if I take out my calculator, just to make sure. So if I got 28 plus 4.056 plus 1.23. When I put that into my calculator, I actually get 33.286 centimeters. But if I want to give my number to the right significant figures, I'm going to use the 2 to round my answer in the ones place. So the final answer here would be 33 centimeters. So that's how I like to look at it. I like to look at my values, find the last decimal place, write down where the last decimal place is, and then circle the one that has the highest value. And then I know for my answer, I have to round to that place. That's how I sort of like to handle it in these examples. All right, questions about that? Okay.
Yeah, I just found out one that I did wrong.
Okay. That's okay.
2.97. And we added it and I did the wrong. I needed to find out. It's in the ones place. That 84 grams is in the ones. So I just did it wrong. So it's good to go over that.
Yeah, which example was that? I'm sorry.
2.97
Okay.
A. It has the container and the ice cream with the fudge sauce and the nuts.
Okay.
What is the total mass? What was it?
Yeah, let's take a look. I got it here. So a dessert container contains 137.25 grams of vanilla ice cream, 84 grams of fudge sauce, and 43.7 grams of nuts. What is the total mass in grams of the dessert? Now, the interesting part about that question is, do they want the answer in the correct number of significant figures or not? You know, a lot of times in addition, subtraction, multiplication, and division questions, they usually tell you whether they want the answer to the correct number of significant figures. I have to double check the quiz. But I'm pretty sure in a couple, when they asked you those questions, they were pretty specific about, you know, going to the right number of significant figures. Because as you'll see, as time goes on and we do other calculations, from my perspective, it's kind of difficult to tell exactly, you know, how many significant values, significant figures each and every value has. You know, so hopefully, I don't think we'll go into that level of depth. I would have hoped in the question, and they didn't, that they would have said, you know, give the answer to the correct number of significant figures. But if they did, then essentially you would have to use the number 84 as sort of the measuring stick, because for 84, the last decimal place of the number is the ones place. And out of the three numbers
like the
given,
example you gave.
that's the highest value. So in essence, if you wanted to give the number there to the correct number of significant figures, your answer should have to be rounded to the ones place based on the technique that we just talked about.
Okay.
All right. So that was addition and subtraction. So for multiplication and division, your answer should be to the number of significant figures as the given number with the smallest number of significant figures. So this is a little bit different, because essentially what you're going to do here is you're going to look at each number that's given, and you're going to figure out how many significant figures each given value has. Whichever one gives you the smallest number of significant figures total, whether it's 1 or 2 or 3, your answer is going to have that number of significant figures. So for example, if you had 56.8 grams times 0.37 grams, the first number has 3 significant figures. All the numbers there are significant. The second number only has 2 significant figures. The 3 and the 7 there are significant, but the 0 is not. Why is the 0 not significant? The reason the 0 is not significant is because it occurs before the first non-zero digit. So my answer, and we'll figure it out in a moment, should only have 2 significant figures. So it's not, and for multiplication and division, it's not based on what decimal place the given numbers go to. It's based on the number of significant figures each of those numbers have. So if we multiply 56.8 times 0.37, I come up with 21.016 grams. And if we're going to have 2 significant figures, that means I'm only going to include the 2 and the 1. So I'm going to have to use the 0 in the 10th place to round. And because it's a 0, I'm going to leave my answer as 21 grams. Questions about that? Here's one thing a useful thing to keep in mind, I think. Because when I think about multiplication and division, let's say for argument's sake that instead of multiplying the 56.8 times 0.37 grams, suppose I multiplied the 56.8 times 3.0 grams. Now the 3.0 still has 2 significant figures. So my answer should still have 2 significant figures. But when I multiply these numbers, I come up with 170.4 grams. Now here's the dilemma. The dilemma is, how could I write that with only 2 significant figures? Because I can't write 17 because it's not 17, it's 170.4. So in this case, from my perspective, you'd have 2 options. What I would suggest to do would be to actually write the answer in scientific notation, just using the 1.7. In other words, using the 1 and the 7 and using that as the coefficient. So what I would have here is 1.7 times 10 to the second grams. And that would come out to 170, which is pretty close to 170.4. What that does is that it allows me to write that answer in 2 significant figures. The other thing you could do in theory, but I don't think I'd recommend this too much, is to actually leave out the decimal point. Because technically, if you leave out the decimal point, you'd only have two significant figures there. I don't think I'd recommend that. I think the correct way to do it would be to put the number in scientific notation. So that's a common sort of thing to solve. Sometimes you get a big number where you can only have two or three significant figures. And the way to get around that is to write the number in scientific notation. So I always like to point that out from time to time. All right, questions about that? All right, so let's just do one or two examples to see if we're good. All right, let's see what we got. So we'll do 2.28. So we'll start with, this will be 2.28a. So we'll do A, and this is 400 times 185, right? Perfect scenario of where we have a major dilemma. Because if you take a look at these two values, the 400 has one significant figure. The 185 has three significant figures. So my answer should only have how many significant figures? One. When I multiply these two numbers, I come up with 74,000. How the heck do I write that in with one significant figure? In reality, the only way to write that with one significant figure would be 7 times 10 to the 1, 2, 3, 4 power. I can't even put 7.4 because that would have two significant figures. I can't put 7.0. I basically just have to write 7 times 10 to the 4th. So this is sort of a perfect case scenario of that particular issue. All right. Questions about that? All right, let's do one more. Just want to take a look at D. So we've got 3.5 times 0.261 over 8.24 times 20.0. So my recommendation for doing this would be to be good with the calculator and to really almost put it all in at once using parentheses with the calculator. Calculators have parentheses that would allow you to do the numerator and then input the denominator and have the division done after you multiply them. If you wanted to multiply the numerator, multiply the denominator, and divide, I think you should still come up with the right answer. But what you'd want to do is go to a couple like 1 or 2 decimal points further than what you would have in your answer in terms of significant figures. Because if you think about what we have here, based on the numbers that are given, our answer is only going to have 2 significant figures. Because the 3.5 has 2, the rest of them have 3. So our answer can only have 2 significant figures. So what I would do is, with my calculator, I would do 3.5 times 0.261, and that gives me 0.756. Then I would divide that by parentheses 8.24 times 20, close the parentheses. So that gives me 164.8 for the denominator. And then I hit equals, and I come up with 0.004587. And I would stop at that point. Now, for two significant figures, we don't necessarily have to write this number in scientific notation. Basically, what I would want to do is I'd want to round using the 8. I want to keep the 4 and the 5. The zeros are not significant. So the 4 and the 5 are. But because I have an 8 here, I'm going to round the 4, 5 up to 4, 6. So I would come up with 0.0046 as my answer. Again, if you wanted to do numerator, denominator, and then divide the two numbers, just go out a few decimal places, just to be careful of the rounding that you do. All right, let's jump quick to number 30, 230. Let's take a look at A, which is 5.08 grams plus 25.1 grams. So here, if I look at these two numbers, for 5.08, the last decimal is in the tenths place, sorry, tenths, hundredths place. 25.1, my last decimal is in the tenths place. So when I add these two numbers, my answer needs to go to the tenths place. So when I put these two into my calculator, 5.08 plus 25.1 I get 30.18, but since I can only go to the tenths place, I want to round using the 8, so I would come up with 30.2 grams. And then let's just do one more. So letter C, 24.568 milliliters minus 14.25 milliliters. So if I take a look at these two numbers, for the first one, the last decimal is in the thousandths place. For 14.25, the last decimal is in the hundredths place. So my answer has to go to the hundredths place. So when I subtract these two numbers, 24.568 minus 14.25, I come up with 10.318. So again, I'm going to use the 8 to round here, and I'm going to round up. So that gives me 10.32 milliliters as my answer. All right, any questions about adding, subtracting, multiplying, dividing with significant figures? All right, so let's take a look at some problem solving using conversion factors. Okay, so you saw in chapter 2, there's a lot of different equalities relating units to each other. As I mentioned, I think it's kind of crazy to memorize all the equalities that were given. So as I wrote in the announcement, you know, the ones I expect you to memorize involve kilo, nano, pico, you know, centi, milli, those ones. But I mean, I think to start memorizing quarts to milliliter, get pints to milliliters, pounds to grams, things of that nature, it's a lot. And for those questions, I looked at the quiz and can provide conversion factors that are needed, but we got to be able to know how to use them. So essentially, keep in mind that any equality can be written as a conversion factor. And remember, in mathematics, how do we recognize equalities? We recognize equalities with equal signs. And a conversion factor is an equality written as the form of a fraction. And essentially, any equality can be written as not just a conversion factor, it can be written as two conversion factors. Because essentially, for your conversion factors, you have fractions that are given that can be written out. And remember, your fractions have two parts. You have a numerator and you have a denominator. And because either part of an equality can be either part of a fraction, essentially that's why there are two conversion factors possible for any equality. The trick to problem solving is to identify the unit given in the question and the unit you need to solve for. What does that do? That helps you identify what equality you need to use, because that's really the first part of it. And maybe sometimes you have to use multiple equalities. But what you want to do is you want to identify the unit that you're given and the unit that you need to solve for, to identify the equality or the equalities that you need to solve the problem. What should happen as you go along is that units should cancel out. And at the end of the day, the only unit that you should have left is the unit you need to solve for. Most of the time, the problems you'll have to solve really involve only using one equality. But as you saw in some of the problems, if you have to go from something like kilograms to milligrams, my suggestion would be to use two equalities. The first one going from kilograms to grams, and then the other one going from grams to milligrams. Now, if you were going from kilograms to milligrams, in the first conversion, you would want the kilograms to cancel out to leave you with grams. And then in the second conversion, you would want the grams to cancel out to leave you with milligrams. So for example, if you wanted to convert, let's say 0.00025 kilograms into milligrams, the two conversion factors we'd have to use is 1 kilogram equal to 1,000 grams. And then I would also use 1 gram is equal to 1,000 milligrams. So I would expect you to be able to come up with those equalities. Remember, kilo means increase by 1,000. Remember, milli means decrease by 1,000. But if you watched the video from last week or was with me, we talked about how equalities don't like decimal. It's better to use equalities that don't have decimals or fractions or things of that nature. So, these are the two equalities that I would expect you to come up with. So in essentially the first step, we would take the 0.0025 kilograms and multiply it by 1,000 grams over 1 kilogram. And I know that's correct because when I multiply, what's going to happen to the kilograms? The kilograms should cancel, which is exactly what we want to have happen. And then for the second step, I would multiply by 1,000 milligrams over 1 gram, because in this step, I want the grams to cancel. Because in my answer, the only unit that I want to be left with is milligrams. And when I set it up this way, remember, when you have like terms in a numerator and denominator, the like terms cancel each other out. So the kilograms here would cancel each other out, and then the grams would cancel each other out. So the only unit that you're left with is the unit of the milligram. So move the decimal point 3 places first. So 1, 2, 3, and then move it another 3 places, 1, 2, 3. So I believe we come up with 250 milligrams as our answer. And I'm going to check because it's probably a good idea to do so. And yes, so 250 milligrams would be the answer here. All right. So let's do a couple of examples. All right. So let's start with 256. Let's start with letter A. So we have 4.82 times 10 to the minus 5th liters, and we want to convert that to pico liters. Pico liters. So what does pico represent? Essentially, and I'm pretty sure pico is 10 to the minus 12th, but since I haven't seen pico in a little bit of time, I'm just going to, yep. So yeah, so pico essentially means 10 to the minus 12. So essentially, 1 picoliter would be equal to 10 to the minus 12, or I should better write that as 1.0 times 10 to the minus 12 liters. Okay. Now, if you wanted to use the equality in this form, it's absolutely fine. Just like I don't like to have decimals, fractions in the equalities, I'm not so much of a fan of numbers that are scientific notation with negative exponents. So essentially what I would do in this case is I would divide both sides by 1.0 times 10 to the minus 12. And what I should come up with is 1.0 times 10 to the 12th picoliters is equal to 1 liter. Okay. So 1.0 times 10 to the 12th picoliters is equal to 1 liter. All right. But either equality would be perfectly fine. You should come up with the right answer. So then what I would do is I would say, okay, 4.82 times 10 to the minus 5th liters. Now let's say I'm going to use this equality right here. So what's going to go in the numerator? What's going to go in the denominator of the conversion factor? We want the liters to cancel. So I would do 1.0 times 10 to the 12th picoliters over 1 liter. Because when I multiply, what do I want to have happen to the liter? I want to have the liter cancel. Okay. And then definitely want to use a scientific calculator to multiply these two numbers. And when I do, I should come up with 4.82 times 10 to the 7th picoliters. But let's just double check that. So 4.82 times 10 to the minus 5th times 1. So 4.82 times 10 to the 1, 2, 3, 4, 5, 6, 7. Yep, 4.82 times 10 to the 7th picoliters. Okay. Questions about that? Definitely want to have a scientific calculator. I can't give you, what I always tell my students is that I can't tell you exactly how to plug the numbers into a scientific calculator because scientific calculators are different. So what I would say is that, as you're practicing, before you take the quiz, if you have questions, send me an email with a picture of the calculator that you're using, and then I can give you the steps of how to do scientific notation and such like that. But unfortunately, scientific calculators are different, so I can't tell you exactly how to use your calculator. All right, let's take a look at another example. Here, all right, so let's do let's do letter B. So let's do 575.2 decimeters to kilometers. All right, so to do this, from my perspective, I'd want to remember two equalities. Because I'm going to think
I'm sorry,
about,
what number are we on?
this is still 56. 256.
Okay, I forget okay,
That's
thank
okay.
you.
No problem. So in my mind, what we'd want to do is we'd want to do decimeters to meters first. And then we'd want to do meters to kilometers. I think for me, based on the fact that I have to remember the equalities, this is probably the simplest way to do it in my particular mind. So the two relationships are that 1 meter is equal to 10 decimeters. And again, that would come from the fact that 1 decimeter is equal to 0.1 meters. But again, I don't like to use decimals and such, but these are the same. But this is the one that I would, from my mind, I'd probably remember that one. And then from meters to kilometers, I'd have 1,000 meters is equal to 1 kilometer. So to solve this problem, these are the two equalities that I would want to use. So let's set it up. 575.2 decimeters times 1 meter over 10 decimeters, because that's going to be great, because that's going to make the decimeters cancel. And then I'm going to multiply that by 1 kilometer over 1,000 meters. Because at that point, I want the meters to cancel. So we're going to end up moving the decimal point. And again, I would use a calculator to do this. We should move the decimal point 4 places. So I should end up with 0.5752 kilometers. So meters to 1, 2, 3. Yeah. So just double check. So 575.2 divided by 10 divided by 1,000. Yep, 0.05752 kilometers. All right, questions about that?
Yeah, so this one doesn't tell us what significant figures, or do we just keep it as that right there?
Yeah, I mean, I would, because I mean, I guess in theory, if you wanted to do significant figures, your answer should only have 1, because you have 1 meter, 1 kilometer as it's written. But from my perspective, like with these questions, you don't usually see them rounded to the right number of significant figures, in a sense. That's why I think the question should really, in my mind, say whether the answer should be rounded to the correct significant figures or not. Because when you're using equalities, equalities are exact numbers in a sense.
Right.
So here, yeah, I would really leave it as 0.05752 kilometers. I just wanted to maybe just check one thing quick about the exact.
Yeah, I wrote down the questions for the homework.
Sure.
And most of them did give, they said 2 significant figures, 3 significant figures.
Yeah.
So that's what the test is going to be like.
Yeah, exact numbers are not measured, do not have a limited number of significant figures, and do not affect the number of significant. Okay, so the thing is that the equalities would not impact the number of significant figures in the answer. Because essentially, significant figures are all about measured numbers. They're not about exact numbers. The numbers in equalities are exact numbers. So I guess if you were asked to solve this to the right number of significant figures, the only thing that would impact the number of significant figures is the 575.2 decimeters. And the fact that that has 4 significant figures and you're doing multiplication and division should lead to an answer that has 4 significant figures. And it just so happens that when we wrote our answer here, it has 4 significant
It
figures.
does.
Yeah,
Okay.
it does. You know, I haven't looked at every quiz yet, but as I said, from my experience, you know, it gets harder and harder to keep the number of significant figures. What I noticed in some of the questions is that they say round to a certain place, and that's okay. Like if they give you that type of direction, then to me, that's enough information to help you get the right answer. You know, I think if they want that or they want the right number of significant figures, it has to state that, in my opinion. So I'll look it over as soon as I can. But I'm pretty sure when I looked at the quiz, the questions that required that said it, and then the other ones, you know, I think, you know, there's a little bit of rounding involved, but a little bit of leeway involved as well. And I think a good chunk of them are multiple choice also, so that'll help as well a little bit. All right, other questions? All right, so let's take a look at 58 for a couple minutes. So here we have some conversions to some different units. Same type of measurement, but different units. So the first one is 0.21 pounds to grams. So again, this is not something I would expect you to commit to memory. But what are the equalities that I would give you to help you solve this problem? Well, basically, the one equality that you would need to solve the problem would be that 1 pound is equal to 454 grams. So if I give you this information, from my perspective, I think you should definitely be able to solve the problem. So let's take the 0.21 pounds, and we're going to multiply it by this equality as a conversion factor. So what's going to go where? 454 grams are going to go in the numerator. The 1 pound is going to go in the denominator. Because when we multiply, we want the pounds to cancel, and they would. So if I take 454 and multiply it by 2.1, I get 95.34 grams. Now, if the question does say to the right number of significant figures, it would all be about the 0.21. And since we're multiplying and dividing, then our answer would only have 2 significant figures. So if we were looking at the significant figure part, then I would technically write the answer as 95 grams. But to me, 95.34 should be acceptable as well. All right. Let's take a look at one more. Let's take a look at letter C. 0.15 quarts to milliliters. Okay. So let's take a look at the equalities here that we would want to give you. So here's the one that I would give you. I would give you 1 liter is equal to 1.06 quarts. Now, if you think about it, is that the only equality that you need to solve the problem? And the answer is actually no. There is a second equality that you need, but this is an equality that I would expect you to have memorized. Because based on, and how would you know that you need the second equality? Well, if I look at what I'm given, I should be able to tell very quickly that I can convert quarts to liters. But my answer, I don't want my answer in liters. I want my answer in milliliters. So what I'm thinking to myself is, I can go from quarts to liters, but then I got to go from liters to milliliters. So what's the other equality that comes into play here? It's 1 liter is equal to 1,000 milliliters. And that one I would expect you to know. And I would expect you to be able to realize that to get the final answer, that equality has to be used as well. So let's take the 0.15 quarts and multiply it by 1 liter over 1.06 quarts, because that's going to cause the quarts to cancel. And then I'm going to multiply that by 1,000 milliliters over 1 liter, because that's going to get the liters to cancel. So 0.15 times 1,000, and then we'll divide that by 1.06, and I come up with 141.51 milliliters. Now, again, if we were looking for significant figures, it would all be about the 0.15, which only has 2 of them. So I would actually write this answer as 1.4 times 10 to the second milliliters, because my answer would only be able to have 2 significant figures. That's why, to me, when I have 141.51 and this would only give me 140, it's not as close as it should be. So that's my gripe, I guess, with significant figures is, the amount of rounding I have to do here to round from 141 to 140, I shouldn't necessarily have to round that far. I shouldn't have to round to the tenths place. I should be able to round to the ones place, the tenths place or the hundredths place. So that's sort of my argument to why, sometimes significant figures are, they cause a little bit of a big rounding issue, so to speak. And sometimes that's why they're put to the back burner, for lack of a better term. Questions about equalities and such like that? All right. I'll just ask, does anybody have any other questions in terms of chapter 1, chapter 2, and such like that? Okay. All right. So if you do, again, before the quiz, just let me know. As it says, the quiz has got to be completed by Sunday at 11:59. Make sure you have a calculator with you, and make sure you have a blank piece of paper as well. This way you can write down, if you have to do some work to solve the problems, make sure you do that as well. This way you have those available to you. All right, and I wish you the best of luck.
Thank you.
You're welcome. All right, and hopefully we'll see everybody next week, and we'll do some chapter 3 work with matter and energy.
Alrighty.
All right, stay well, everybody.
Thank you.
You're welcome. Take care.